we will discuss the unchecked variability OCV, including the local OCV, in a transistor mismatch, which we should accept and design for it. But usually, people only simulate or verify the local variability without any design insight. Therefore, we should know why designing error blocks for LOCV efficiently. Besides understanding why the LOCV occurred, another important exercise in the circuit design is by observation exercise, which Paragon did a really good job and became very useful for decades. From the reference, you will realize that Paragon noticed a remarkable trend in 1989 that the mismatch could be exploited across a huge range of technologies from a single parameter, which is the transistor oxide thickness. According to our sanity check, the trend amazingly ballpark holds down to 7 nanometer as the T oxide equals 1 nanometer and AVT equals 1 millimeter. Again, thanks to Paragon's observation, we now have a simple model for the threshold voltage variability, such that we not only can think intuitively, but also have a simple hand calculation in our design flow. First, we should model the threshold voltage variability of a transistor by a voltage source in series with the variable RMS value sigma Vt in series with the gate of the transistor. Second, the AVT should be found in each technology, which again depends on the transistor oxide thickness to 1 millivolt T oxide in nanometer. Third, or finally, the sigma Vt should be a function of the transistor area, W times L, assuming the local mismatch is dominated here. After finishing the simple model for the threshold voltage variability, we can exercise those error blocks easy. Let's start. To be clear, the current meter mismatch could come from several factors we mentioned, but we are referring to the threshold voltage variability impact on the current mismatch for now. For example, we could determine the values of sigma Vt1 and sigma Vt2 given by area and technology easily. Then, in the design exercise for a given sigma Vt, you should know what the current variability in RMS value is. In addition, you may also know the percentage of variability to the average current in RMS value by a simple sigma Vt divided by the overdrive times 2. Then you can quickly know if your designed DC operating point is making sense to meet the specification of the current variability. In this simple variability image, do you know how to reduce the variability through your design overdrive? Correct. Increasing the overdrive voltage leads to a less dependency on the current variability from the variability of the threshold voltage. Another popular tool of the DC operating point is the GM over ID, and it should be minimized to reduce the current variability, because sigma ID equals to sigma Vt times GM over ID. If you try your best to either maximize the overdrive or minimize the GM over ID, what else can reduce the current variability? Bingo! We are circling back just to reduce the variability of the threshold voltage itself. Remember the sigma Vt equals the LVT divided by the square root of area, then the transistor area should help reduce sigma Vt. Again, thanks to Pergun's observation that the LVT can be obtained easily, but if we would like to know if a 2 nanometer design can fit Pergun's LVT observation, how can we do it? Right, you can reverse engineering by observing the current variability through a diode-connected Monte Carlo simulation to either sanity check the Pergun's LVT or obtain accuracy in any advanced technology. So, the methodology for determining the LVT is to measure the threshold voltage variability on a diode-connected transistor to get the sigma Vt. For example, the LVT equals the known sigma Vt times the square root of W times L. Then you can just use the calculated LVT to do your other hand calculation in other algebra blocks for first order design exercise, instead of blindly simulating any undesigned blocks. Finally, how do you verify the local variability precisely? Bingo! The most popular and precise way to verify the local OCV in your algebra block level is through the Monte Carlo simulation as well. Any foundry should provide the variability information in their SPICE model, such that the circuit designer can run the Monte Carlo simulation in any simulation tool to get their design precisely in the variability. Again, the Monte Carlo simulation of the final algebra block level should be a final sanity check of your initial hand calculation instead of your initial design. Otherwise, you don't have any intuitive image in your own design block. Make sense? Here are a few summaries of why we need to design algebra blocks for LOCV efficiently. To be involved in the design intuitively, you must have an intuitive model on your own, such that you do not rely on any simulation tool. The first amazing model is from Pergun's observation: transistor oxide thickness, determine the LVT and also the variability of the transistor's threshold voltage. Then, the simplest algebra block is the voltage control current source, which shows the threshold variability leads to the current variability intuitively. So, we must do our current source mirror design through the hand calculation easily, without relying on any simulation tool. Interestingly, to obtain an accurate LVT, we can apply a Monte Carlo simulation to a simple diode-connected transistor. Similarly, to sanity check our hand calculation precisely, we still can apply a Monte Carlo simulation to our design block, instead of blindly simulating anything without any intuitive modeling. Again, a simple model to evaluate the LOCV is nice to have to design efficiently without any big mistake. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be benefiting from it.